All right, so in 3.3, we're going to take a look at rates of change and behaviors of graphs. So first things first, when we're determining a rate of change is nothing more than a slope. However, we're looking in this sense at a slope of a graph between two specific points in some type of a graph that usually is not going to be linear. Okay, so that rate of change is possibly constantly changing itself. Okay, now I know there are a few of us in here who have already taken calculus, and we know how to do this via a derivative. But for this class, we are going to be finding rates of change between two specific points algebraically, not necessarily using a derivative. You want to use a derivative to double check that you did it correctly. For those of you who have that experience, you're more than welcome to verify it that way. Okay, so rate of change is defined by the change in y, or delta y, over the change in x, delta x. When we're talking in terms of functions, all right, we have f of x sub 2 minus f of x sub 1 over x2 minus x1, right? Which is equivalent to y2 minus y1 over x2 minus x1, which is nothing more than our original slope formula. So if I want to determine rate of change, so the one example I typically use here is looking at the rate of change of gas prices. Excuse me. The one that I use here is when I graduated from high school in 2000, I was paying $1.25 per gallon of gas. If I want to find the rate of change to today, what information do I need? Well, don't I currently need what the price for a gallon of gas is right now? And I believe when I filled my truck up the other day, because I put 89 in it, I believe I paid $2.94 or $2.95 for a gallon of gas. So let's assume that. So here today we are in 2020, and I paid, let's say it's $2.70 for 87, okay, because most vehicles are using 87. So I want the delta y over delta x, or y sub 2 over y sub 1. Now, which one's x, which one's y? Right? In this case, the price is going to depend upon the year. Right? And the price is dependent upon what year we're talking about. All right? So here I'm going to have 270 minus 125 divided by 2020 minus 2000. So here we're going to have $1.45 divided by 20, and $1.45 divided by 20 is going to give us 0.0725. What's that 0.0725 mean? Well, think about it. Here, my units are dollars per year. So this is the change in price. My price is increasing by 7 cents every single year. Now, had we checked the average rate of change between years back in, say, 2009, 10, 11, 12, when gas prices were really, really high, we would have had a much different rate of change here. The next thing, if we're looking at rates of change given a function h of x, in this case x squared minus 4x plus 5 over the interval -2 through 5. So again, I'm looking at delta y over delta x, and here I'm looking really at h of x sub 2 minus h of x sub 1 over x sub 2 minus x sub 1. So in this case, what I've really got here, I've got my x1 and my x2. So here I'm going to evaluate h of 5 and subtract, and in parentheses I want to subtract the entire function h of -2 over 5 minus -2. So got a little bit of work to do here. So when I evaluate h of 5, I'm going to have 5 squared minus 4 times 5 plus 5 minus the entire function. We're going to have negative 2 squared minus 4 times negative 2 and plus 5. Again, I'll divide it by 5 minus negative 2, or 7. So let's do a little simplification here. So I've got essentially 25 minus 20 plus 5. We're going to have 10 minus, and we're going to have 4 plus 8 plus 5, or 17, divided by 7. So 10 minus 17 is going to give me negative 7 over 7. So my average rate of change over the interval is going to be negative 1. Now, here we're looking at the average mortgage rate. I'm going to get rid of the calculator for a minute. We're looking at mortgage rates, 30-year mortgages over the period 1995 to 2016. And I would even say, and here in red is our 30-year fixed mortgage rate. Okay, that's our normal that we're looking at. In 2017, that average mortgage rate was, didn't want to give me a straight line there. Still doesn't want to do a straight line. It's somewhere around 2.7 or 3.75. There we go. Okay, so our average mortgage rate in 2017 was around 3.75. Those mortgage rates, even in the last 3 years, have dropped significantly. We just refinanced our house at 2.75, and I've actually now started to see some interest rates that are around 2.5 right now. Okay, but if you look back to when I first bought my very first home back in 2009, those interest rates were up here around 6.5. Okay. So really, I mean, if I were asked to find the average rate of change for interest rates from any point here, I could go ahead and do it. So if I was asked, from 2000, in April of 2000, to figure out what that interest rate was, I can draw some nice straight lines, kind of figure out where those points of intersections are. All right, and I could say, well, I think that interest rate in 2000 was around 8.6% or so. Okay, and I could do the exact same thing that we did just a few slides earlier between any 2 points on this graph. It would be the exact same process. Now you're just taking that data from the graph before you can actually plug some numbers in. You have to interpret the graph first. And we'll talk a little bit about interest rates in class physically. All right. So local minima, local maxima, and intervals of increasing and decreasing. So a function is increasing on some interval a through b if f of b is greater than f of a, right? Assuming that b is greater than a. So essentially I'm moving from left to right from a to b, and my y value is then f of b is greater than my y value at f of a. Okay, thus I would have an increasing function here. Okay, a decreasing function then, again, if I have 2 points, say a and b, where b is greater than a. So again, I'm moving from left to right. We're always talking left to right whenever we're discussing increasing or decreasing. If f of b is less than f of a, then I have a function that is decreasing. We have a local maximum at a point here for the definition. We're going to say at the point b, when f of b is greater than all f of x for values from some interval that contains b. So in this case, in terms of the graph, from a through c, f of b is the highest point, right? F of b is the largest value. Thus, it is a local maximum because f of b is greater than all of the other values f of x on the entire interval from a to c. I hope that makes sense. Likewise, we would have a minimum if f of b were the lowest value on that interval from a to c, so lower than or less than all f of x in the interval. So absolute max and absolute min really are kind of the same definition, but instead of saying a specific interval from some point A to some point C, now we're saying for the entire domain of the function. So we have a maximum of f at a point C if f of C is greater than f of x for all x in the entire domain or in the entire graph. Same thing, we have a local minimum, or an absolute minimum rather, at a point D if f of D is less than all f of x for every x in the domain of f, right? So we take a look at the graph that I have over here. So let me start with the local max. So here, at the point that's, roughly, let's say, I don't know, 0.75 and 4.25, we have a local maximum. Okay? I have a local minimum. Switch to a different color here. I'm going to have a local minimum at this point here, which is 2, 0, because everything to the left and to the right of it, this is the lowest point. Thus, it's a local minimum. Now, assuming this graph goes up on both of these tails and continues and it never turns and comes back down, right? Then we would say that we have a local maximum down here at this point, negative 0.593 and negative 3.246. Okay? This is the lowest point on the entire graph. Thus, it's our absolute minimum. Okay? Let's talk about intervals of increasing and decreasing. Okay? Interval of increasing or decreasing is essentially where I have, if my graph, as I move again left to right, if my slope is negative, or if my y values as I move left to right are decreasing, then I have a interval of decreasing. So let's do intervals of increasing, and we'll do intervals of decreasing. So let me go through here, and along this interval here, my y values are decreasing. Along this interval here, my y values are decreasing. Right? My slope is negative, thus I'm going to have a interval, or a area where my graph is decreasing, and I should have highlighted that in blue. So let me go back and do that in blue. Forgot to switch color. So my graph, my slopes are decreasing here, right, along this interval, and also here along this interval. Now, whenever we talk about intervals of increasing and decreasing, we're always talking about intervals of x values. So in that first interval, I'm going from negative infinity all the way down in terms of my x values through negative 0.28. Union with, and then my second interval is going to be 1.78 through 3. For my intervals of increasing them, I'm going to be increasing from negative 0.28 through 3 along this interval. And I'm also going to be increasing from 3 through infinity. Now, when we're talking intervals of increasing and decreasing, again, it doesn't matter how high, how low the graph is, it doesn't matter what the y values are. The part that is important here is over what interval of x does the behavior occur. When you're asked for this on a test or a quiz, or whether it's on a standardized test, SATs, ACTs, something like that, you're always giving, in this case, the interval of x values over which the particular behavior they're asking for occurs. Okay? It does not matter what the y values are. I want to know over what interval of x values does the behavior occur. Okay? My local max is going to be at 1.78, 3.23 if I round. I'm going to have a local min at 3.0, and I'm going to have an absolute min at negative 0.28, or 2.2, I can't speak, negative 0.28 and negative 9.92. The last thing here, and we're just going to talk about it, and then we'll move on. So the difference between sketching and graphing functions. So if you're asked to sketch a function, maybe a quadratic, all right? I'm looking probably for the vertex to be in its exact proper position, and then a good representation or generalization of what the shape of the graph roughly looks like. Okay? It shouldn't be sloppy, but it doesn't need to be precise. If, however, you're asked to graph a function, then I'm looking not only for, for a quadratic, for example, for that vertex to be in its exact position, then I'm looking probably for the other 5 critical points, or at least a series of other points that are precise, whether you come up with them by hand, whether you find them from the XY tables using a graphing calculator, but I'm looking for precision with multiple points plotted. So again, if I'm asking for something to be graphed, I'm looking for multiple points in their exact locations. If I'm asking for a sketch, I'm probably looking for just the vertex or the locator point in its exact position, and the rest of the points just generalized, you're getting a good rough shape of that graph. So essentially it all depends on the purpose and what we're using it for, whether we need to have a sketch or a graph, and we can discuss that a little bit more face-to-face in class. But for right now, on the video, I'm going to leave it at just the difference of sketching and graphing. We're going to do a little bit of graphing practice when we see one another in class tomorrow. So with that, I'm going to leave you guys to it. Take a look at some of the problems that are coming up. Make sure and maybe try 1 or 2 of the problems. Maybe an even that's not actually assigned for work, in terms of finding intervals of increasing, decreasing, and the local max and mins. That way we can check it and kind of go over it when we see one another tomorrow in class, and we can answer some questions then. All right, have a good day, guys.